Welcome back. A roller coaster track has highest points and lowest points. If we know a function that describes the track, how can we find these points? This simple question, how to find minima and maxima of a function, has numerous other applications because it has to do with optimization. Think of economics. A firm wants to know at which output the profit is maximal. Or physics. The stable states of a mechanical system are precisely those for which the energy is locally minimal. Or think again of our roller coaster example. The speed may not be too high due to safety and cannot be too low either, because then the cart may get struck on the track. So when you are designing a roller coaster, you have to know what the minimal and maximal speed of the cart will be. In this video, you will learn how differentiation can be used to deal with such optimization problems. Let me first recall some terminology. We say function f has a global maximum at x equal a if all function values are smaller than or equal to f of a. Similarly, we say f has a global minimum at x equal b if all function values are larger than or equal to f of b. The name global suggests that there are other types of maxima and minima. Well, there are. We say that f has a local maximum at x equals c if fc is the largest value that f attains on some interval around x equals c. Similarly, we say f has a local minimum at x equals d if f of d is the smallest value that f attains on some interval around x equal to d. Note that this also holds for the global maximum and minimum. Those are special cases of local maxima and minima. By the way, sometimes I get tired of saying maximal values and minimal values and simply call them extremal values. What do these extremal values have to do with differentiation? Well, recall the following. If a function is differentiable and the derivative is positive, then it is increasing. If the derivative is negative, it is decreasing. Now, at a local maximum or minimum, f is neither increasing nor decreasing, so the derivative is precisely zero at those points. Indeed, let's look at a local maximum in the graph in the picture and zoom in. If you pass over a maximum from left to right, then just before the maximum, the slope is positive, and right after, the slope is negative. Precisely at the local maximum, the slope is zero. Based on this, you may suspect the following. Given a function f and a point a where f has an extremal value, the derivative of f at a equals zero. Let me stress here that this is not always the case. Look at the following example, the absolute value of x. This function is has clearly a minimum at x equal to 0. But what is the derivative there? As we have seen in the previous video, the derivative does not exist there. So we see maxima and minima can also be attained at points where the derivative does not exist. Okay, so now you may suspect the following. In local maxima and minima of f, either the derivative vanishes or it does not exist. Even that is not always the case. For example, look at this picture of the famous Gateway Arch in St. Louis, USA. Its height, as a function of horizontal position, is a differentiable function. At the highest point, you see that the derivative of this function is 0. Nothing extraordinary there. But what about the lowest points? Clearly, the lowest points are at the feet of the arch. The height function is differentiable there, but the derivative is not equal to 0. So what's going on here? Well, we are talking about points at the boundary. At boundary points, a function can have a local maximum or minimum without vanishing derivative. Okay, let's gather what we have seen. If f attains a local maximum or minimum at x equal to a, then either f prime of a equals 0, or f is not differentiable at x equal to a, or x equal to a is a boundary point of the domain of f. And this is indeed the full story. Let me introduce some extra terminology. Points on the horizontal axis where the derivative of f is 0 are called critical points. Points where the derivative does not exist are called singular points, and if a point is at the boundary of the domain of f, it's called, naturally, a boundary point. A warning is in place here. It is a common mistake to use this result in the wrong way. It says that if f is locally extremal at x equal to a, then x equal to a must be a critical point, singular point, or boundary point. But the other way around is not necessarily true. For example, if the derivative is 0 at some x, then the function does not necessarily have a local minimum or maximum there. A standard example is the function x cubed. The derivative is equal to 3 times x squared, which is 0 at x equals 0. So this function has a critical point at x equal to 0, but it has no extremum there. It is increasing for both x smaller than 0 and x larger than 0. Similarly, a function can have singular points which are neither a local maximum nor a local minimum, as the example shows. Keep that in mind. Let me summarize. If you want to find local extrema of a function, first find the critical points, singular points, and boundary points. If the function has local extrema, then it must be at those points. So we have limited our search from the whole domain of f to a limited set of points. But keep in mind, we still have to investigate the function at each of those points to see whether it has a local maximum or a local minimum, or neither. You will see tips and tricks for that in the rest of this subsection. Let's practice.